Lecture 2.7, Heating and No Temperature Change, Latent Heating. As we saw in lecture 2.6, there was a flow chart. So I'm just going to I copied it and I'm going to paste it right here. So now what we're doing here is that we're changing directions. In specific heating, we change the microkinetic energies. With latent heating, we change the micropotential energies. So what we're looking at here is that latent heat is when heating goes completely into U-micro. And U-micro, this is bond breaking or bond forming energy, not KEmicro. So if KEmicro does not change, temperature is equal to a constant. So if I was to write this slightly different, I would then say that latent heating solely goes into breaking molecular bonds, causing a phase shift or a phase change of a material. Now, there's lots of phase changes. By the way, latent heat does not apply to ideal gases because an ideal gas has no bond. So the common ones are, one, if you go from a liquid to a solid or back from a solid to a liquid, we call this latent heat of fusion. The other one is that you can go from a gas to a liquid or from a liquid to a gas. This is called latent heat of vaporization. And in some situations, which are not common to us, you can go from a gas to a solid or from a solid to a gas. This is called this latent heat of fusion of sublimation. So there are other phases too. I mean, you could go from a fluid to a superfluid, or you can go from a conductor to a superconductor, but these require quantum physics to explain and beyond the level of this course. There's lots of other phases that we can look at, but not in this course. So then we asked the simple question: how is it that there is no temperature change while heating occurs? Right? That's a pretty important question because that really separates the two types of heatings. So one of the things that you have to consider before anything here is this. Any, let's say, ice water mixture must have the ice and water at 0 degrees Celsius at its maximum temperature. So what do I mean by maximum temperature? If I have an ice water mixture, it has to be at 0 degrees Celsius. That's the maximum temperature that ice can exist in. If it's at 20 degrees Celsius, for example, it's not, there's no ice. Like another thing that you should consider here is that ice from an ice maker that comes directly out of your freezer is at minus 20 degrees C. So when I say I have an ice water mixture, most of the time I'm talking about 0 degrees ice. There is a difference, and we'll get to those details as we go along. So now let's look at an example. As an example, I'm going to consider an ice lemonade mixture. And since lemonade is mostly just water, then I have an ice water mixture. So consider an ice lemonade mixture that sits on a table. Let's say a table in your kitchen. So we could make a couple of remarks. We already know that as the ice melts, the ice lemonade mixture remains at 0 degrees C. Even though heating is occurring. So what do I mean by that? Well, let's imagine that I have a glass of lemonade. Let's say that this is my glass. And these are some ice cubes. Maybe I have an ice cube here. And these are my ice cubes. So what I'm seeing here is that the lemonade is right here. And what you're seeing here is that what you're finding here, this guy must be at 0 degrees C. Now let's say that we're at room temperature. Even though it's 20 degrees C, let's say room temperature, I do have heat that is flowing into the glass. And we can say here is that clearly this is the direction of heat transfer. So even though there's heating, the ice does not melt. So what, just to repeat what I just said here, that because the room is warmer, in this case, 20 degrees C, then the iced lemonade heat transfer occurs into the glass. So then, here we go. Where does all this heating go to? Well, here's what we know. The internal energy reads that all of the heating has to go into changing the internal energy. We already know that the change in potential energy and the change in the micro potential energy. But we could say here is that if there's no change in temperature, right? This tells us no change in temperature. In other words, delta T, the change in temperature, is 0. We have no other choice but to conclude that the heating changes the micro potential energy only. And if it's breaking, if that's the case, what's happening, then what you're seeing here is that this heating is breaking ice bonds. That is, this type of heating breaks bonds. And that's what we mean by changing potential energy. So when I look at this thing, what you're really seeing is that you're seeing a phase transition. This is the process of melting ice. So if I have solid ice, then the process of latent heating, its whole job then is to break bonds. And in this case, it breaks ice bonds into liquid water. There is a phase change that occurs. So let's define latent heat of vaporization. Okay, so then latent heating is the heat of transformation that changes the phase of a material. So when I look at this thing, here's the language is really bad. This is called the latent heating. And sometimes you'll see me write this as QL, but heating is heating. Heating is just the transfer of energy. And then what you're going to see here is it's mass dependent. And then there's this guy, L, where L is the energy required to break bonds per unit mass. And I'm going to have to come back to that later after we explain a little bit more, because the wording on this is atrocious. And if you don't realize, they also call L latent heating, but it's more complicated, as we'll find out right now. Okay, so I'll explain the language here in a minute, but let's just look at the units first. So unit wise, so if I look at the units, you can see here that I have Q is equal to ml. So that immediately tells you that the units of L is then the unit of heat divided by a unit of mass. So it's joules per kilogram. So now let's interpret what we're seeing here. So this is a very light interpretation. So let's just interpret latent heat. In a moment, I'm going to get into it deeper, but I just wanted to just be very light before we get into it much deeper. So the first thing that we should say is the latent heat, that's this parameter L, is material dependent. So different materials require different amounts of energy to break molecular bonds. So one way to think of it, it turns out that liquids have a, like, so for example, it takes a lot more heating to break liquid bonds to become water vapor. And water vapor, of course, is a gas. Then breaking ice bonds to become water. So in other words, so if I look at the latent heat of going from a liquid to a gas, in general, almost always, I can't think of a single case where this is not the case, that latent heat from going from ice to water is smaller. So latent heating is a unique value for each material, since UMicro is also unique. And what we'll find here is that there are essentially 3 phases. And we already talked about them. The 3 phases, I think we said them, they're going from a liquid to a solid, a gas to a liquid, and a gas to a solid. So those are the 3 common phase transitions that we see. Now, another thing that we should talk about here, we can see here that the other thing that latent heating does, we see that latent heating and this is where I define this as QL, but remember, it's really just Q. This is equal to mass times the latent heat, which is proportional to mass. So latent heating is mass dependent. So as an example here, it takes a lot less heating to melt a single ice cube versus a large ice block. They're radically different, right? Because if I think about a cube, maybe a cube might look like this, and it's just this little tiny thing, and we say, yep, that's the mass of a cube. But if I take a huge ice block, something like this, which has a much larger mass, then we could say here is that if I compare the latent heat, because if they're both ice, you could see that I'm trying to draw the L's the same. So then this latent heating is going to be small. This one is going to require a lot more heating. So now let's start to physically interpret these things into detail. And as we do this, one of the things that we're going to have to do here is that I'm going to use the applet states of matter. Okay, I'm definitely going to use the applet states of matter. There's some issues with it, but we're going to use the applet because, not because it shows phase transitions, it doesn't, even though it claims it is, it's incorrect. But we're going to use it to look at just slides of what is going on as a visual aid. But I definitely want to do it. So now let's talk about the physical interpretation. Okay, so here we go. So we're going to start off with the first kind of latent heating. So here, this is latent heat of fusion. And here's where the language gets really bad. When they say that, they mean L, not Q. So the language is not good. Okay? And to show you what I mean here, look what they call Q. Now, they call Q latent heat. They also call L latent heat. So what I'm going to do here is I'm going to try to differentiate the words here. So this is going to be M times LF. So what I'm going to say here is that this I'm going to call latent heating, not latent heat. And then typically we identify which latent heat we're talking about. So this would then be the latent heat of fusion. That's the language that I'm going to use. Okay, there's my language right there. So what I want to do here is that let's go in and let's just look at this lightly, and then let's get into the details here. So what do I mean by latent heat of fusion? Well, we have a phase transition. So we have a phase transition. So the transition can go both ways. So I have a solid or I have a liquid. So here's what happens. If I go in this direction, I add heat. And what this heat does is it breaks bonds. If I go the other direction, instead of adding, I remove. And in this process, this is what forms bonds. So the word is loose here, but this is what I mean by that. So I'm going to lower this just a little bit because I want to put a box around this. Okay, so if I put a box across this, because this is a good image to have. So many of our problems will involve ice, water, and water vapor. So what that means here, just like the picture up there, latent heat of fusion is added to ice to break solid ice bonds into liquid water bonds. On the other hand, if I'm going from a liquid to a solid, latent heat is removed to force liquid water bonds to allow solid ice bonds to occur. So what I'm going to do here is that I start to explain this, and one of the things that I said here is that I'm going to use the applet by Fett called States of Matter. Now you can't take this applet too seriously because what ends up happening is that it's not correct. Once again, we're not here to try to say nothing but just look at the images. That's all I care about. So here we go. So now what we want to do here is that we want to do this following thing here. So I'm going to look at ice. So I'm going to look at the ice, water, phase transition. So here we go. So I'm going to go to the applet so you can see what I'm talking about. So let's look at that. So I'm going to share my screen. I'm going to go to my I go here. So this is just for neon molecules. We don't care about neon. We want water. Now, there's a couple of things that you want to pay attention to here. One of the things that you want to look at here is that you can see that I have ice crystals. And when I look at ice crystals, note that these guys are definitely vibrating, but they do form this crystalline structure. Okay, they do form this crystalline structure. Now, and on the other hand, what you're seeing here is that if I now go to the liquid phase, look how the bonds change. So you could see that the kinetic energy is higher, but you're seeing rotations and all of that. They're definitely not any other structure here. So, but that's what we're looking at. So the first thing that we want to do here is that I want to come in and I want to look at this ice to water phase transition. So what I did here is that I just took some images of the screen, and let me go back to share what I have. So these are the images that you just saw right there. And what you're seeing here is that this is ice with crystal structure. On the other hand, this is water with no structure. So what we're doing here is that in order to go from the solid crystalline structure to that, we have to add heat. So if I come back into here, let's go look at this thing. So if I go back to the solid, now what I'm going to do here is that I'm just going to add heat. And there's higher vibrations, and you could see that I have broken the bonds. So by adding the heat, it then goes to a liquid here. Now, because this is very, very sensitive, the reason why this applet is not good here is because this temperature changed. For example, let's go back to solid water. Look at that, that's 146. If there's a phase change, that temperature should not change, but the temperature is changing. And look at that, that's still crystalline structure right there. That temperature is wrong. So if I add enough heat, then I get my crystalline structure right there. So if I go back to my notes here, then this is what we're seeing. We're seeing that the first thing that I got to do here, in order to break that structure, what do I got to do? I have to add heat. What kind of heat am I doing? I'm doing latent heat diffusion. I'm doing latent heating in order to get that structure. So we can clearly see here that latent heat diffusion is added to ice to break solid ice bonds into liquid water bonds. So let's see if I could just highlight very, 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 very quickly. So if I'm going from an ice to water transition, what am I seeing here? We already said that heating is added to break all, and this is the key thing, all the bonds. Now note, you can't break all the bonds at the same time. one cannot break all the bonds simultaneously. That's why the change in temperature is 0. There is no change in temperature. So the way you start to break the bonds, the heat added causes the vibrating ice molecules to have larger amplitudes in their amplitudes. I'm sorry, I just repeated myself. Ice molecules to have larger amplitudes until it breaks apart, which again means no crystalline or crystal structure. Now, the important piece here is that so this is important. So in order to solve homework and quiz problems, we ask this very important question. What does this look like on a T versus Q graph? So what you're going to see here is that when one melts all the ice and it warms up the melted ice, which is wrong, right? Because there's no temperature change. So when one melts the ice, you don't warm up the ice, you start to break one bond at a time. So then the graph effectively gives us two pieces of information: the transition from ice to water, and then the amount of heating required. So let's look at this thing here. So here I go. So what I want to do here, I got to go up. So here we're gonna, so there's two graphs that I want to look at. They're the same graphs, but I want to make sure that I highlight the information. So this is going to be the transition from ice to water. So then what I'm going to do here, I'm going to plot this. So this is going to go 2, 4, 5. And this is going to be my Q. And so here's what happens. Let's say that I start with ice at 0 degrees C. Now remember, that's not normal ice. Ice out of the freezer comes out typically at minus 20 degrees C. So now I'm assuming that I have solid ice. So now what I'm going to do here is that I'm going to start adding heat. Okay, I'm going to start adding heat. So this, as I start to add heat, this now becomes an ice water mixture. And this point right here is what I call the critical point. You know what? I'm going to copy this first because to save time. Okay, so then I'll put this graph right here. Okay, so as I add heat, I'm seeing that the water is melting. And what you're going to see here is that there's this thing called a critical point. So what's special about this critical point, which is this black dot? This is the separation point between water and ice. When you get to this point, it also means that all the ice has now been melted. That's what I mean by that point. Now, if I look at this thing, you're seeing here that this is a key point here. So what I'm seeing here is that my path is going in this direction. I'm going from left to right. And as it goes from left to right, note that there is no temperature change. But the ice is melting. You're breaking one bond at a time. At some point, you're then, after you've heated up, you've melted all the water, then you start to move uphill. And so what this is telling you here, this is the region of specific heating. That means here is that now in here, as you go up, you now take your melted ice water, and now you have completely all liquid water. There's nothing else there. So the other piece of information is that this also tells us about the amount of heating required. So if I look at this thing, if I come all the way up to here, I'm going to say that this guy's going to come, let's say, up like this. So now let's look at this. Again, look at my direction of process. I'm going from left to right. So now what I'm doing here is that I'm heating. I have heat to melt all ice. So if I look at my heat, I have a horizontal bar that looks like this. And because there is no temperature change, this is the amount of latent heat added in order to melt all of the ice, right? So remember, the critical point right here, this is when all ice has melted at that critical point. So I can then say that this is QL, and this is equal to MLF. That's the latent heat of fusion. Now, if I start to warm up the water here, what you're seeing here is that you're seeing what? I then continue to increase the temperature from 0 degrees C to some other temperature. So right here, what you're seeing here is that this is the change in temperature of the water. So when I look at this guy, this tells me that I have a second bar right here. And what the second bar is telling me is that now what I have here is that I have specific heating. And this guy is equal to MC delta T. So when you're looking at this guy, what you're finding here is that this guy right here is a horizontal energy bar diagram. So that's what's happening right there when you're looking at this transition here. So now what I want to do here is that now let's go look at the other transition. If I look at the other transition, let's go from water to ice. So our next transition is water to ice phase transition. So what I want to do is I want to go back to the applet. So let me come in and look at this, and let me go share my. So now let's say that I have a liquid like we're showing right here. So when I have a liquid, what I'm going to see here is that I got to do what? I want to form that lattice structure right there. But this is what I have right here. So what do I have to do? It turns out that these molecules are moving too fast. So now I'm going to start to extract heat. And as I extract heat, note that these crystalline structures have now formed. Again, if you're looking at the applet, I mean, this should not be changing temperature, but you're seeing that the temperature is clearly dropping. So again, that is a problem. So I just copied these images. So I just inserted them into the sheet. Let me go back into this new share. So what you're seeing here is that I just got these things here. So now let me say here is that latent heat of fusion. So latent heat of fusion is removed to force liquid water, I said liquids, but liquid water molecules to allow the formation of solid ice bonds. So when I'm looking at this guy, here's what I have here. I'm seeing here that I'm doing what here? I'm seeing here is that in this case here, this is water with no structure. And over here, this is ice with crystal structure. And the big difference here is that I'm doing what? As I do this phase transition, what am I doing here? I am moving, let's say, in this direction, but this time, what do? I remove heat. In other words, I'm removing latent heat of fusion. So going, just saying this quickly again, here's what we're finding here. So water to the ice transition, what we're seeing here is that the liquid water molecules have too high of kinetic energy. By reducing KEmicro, but remember, KEmicro in this case is also the heating. That's what we mean by negative here. They move with smaller, I guess amplitudes or smaller speeds or whatever until the electrical bonds form. Since water is a polar molecule, it can do this. In other words, that is, heat must be removed to allow the ice bonds to form. So again, the most important thing is, how does this look on a T versus Q graph? How does this look on a T versus Q graph? That's the important piece. So let's look at this. Now, suppose that you how do I say this? You fill ice trays of water into the freezer. What is the path? So again, let's look at what we have here. And in this case, we're going to look at the transition from water to ice. So if I look at this transition, what does it look like on our curve here? So I'm going to go, let's guess, I got to estimate my size here of my graph. Okay, so this is going to be T. And then this is going to be my 0 mark, 0 degrees Celsius mark. So then I'm going to go, let's see. Well, that's a long one. I don't think I made the other one this long, but let's just leave it there. So then what you're going to see here is that what do I have to do? I have to cool the water. I have to remove heat. So then what I'm saying here, then this guy has to go where? Let's say it goes to right here. So this is my path right there. So you can see here that I am decreasing the temperature of the water. So I would think that most of the cold water coming out of the faucet from our experiment, mine was about 18 degrees C. So you're clearly seeing my path as I decrease right here. So what am I doing right here? I'm removing heat to cool water to 0 degrees C. right? That's what I'm doing right here. So then what happens here is that now I start the phase transition process here. So if I look at this thing, this is then going to come, let's say, all the way to right here. And then I'm going to say that this is another critical point. You know what? I'm going to copy this so I don't have to do this again. So let me copy this. Oh, that works. That size works just well. So now what you're seeing here is that you're seeing this. Here's my transition. So now, as soon as I get to this point right here, this is where the water starts the freezing process. In other words, latent heat is now making it where this now becomes an ice water mixture. So as you see here, there's no temperature change. And over here, you see that there is a temperature change. So when you get to this other point right here, I would say right here, when you get to here, then we say that all water is now frozen. So now the question is, let's look at this other part of it. So now this is about the amount of cooling required. So if I look at this thing, I then see here, you can clearly see that this represents a change in temperature. I'm gonna put this in red to just make it stick out. So from here to here, you can clearly see that here's a change in temperature. So if I'm cooling the water, right? So in this case, I'm cooling water to 0 degrees C, then that means I need this amount of heat to go from here to there. So my horizontal energy bar diagram tells me that this has to be the specific heating that goes on. That's what's reducing the temperature of the water. And so therefore, I must use that relationship right there. So once I get there, my path continues to move in this direction. And again, this is my ice water mixture. And if this point right here says that I now have solid frozen water, in other words, ice, then that means the amount of heat that I continue to remove is this amount right here. And so this is the latent heat that we have to take out, which is of course written as Q equals ml. So if I start off at 18 degrees C and I want to freeze all the water, I have to add the specific heating plus the latent heating to do that. Now what I want to do here is that before I finish this chapter, I want to summarize. Okay. So I want to summarize T versus Q graphs for all of the possible phase transitions. Okay, so let's look at latent heat diffusion. So one of the things that we should look at when we start to look at that, let's assume, so I'm going to look at latent heat diffusion. And when I look at latent heat diffusion, I'm going to start with freezer ice, and that's at minus 20 degrees C. And then warm it up to become water. So there's going to, or I could go the other direction too. You know what? In fact, I think I'm going to isolate two cases right here. So I'm gonna do this, and then I think I want to put them on the same region here. Okay, so here's my latent heat diffusion. Okay, so let's do this. So if I look at this thing, here's what I see. Here's my graph. And I'll probably have to organize this a little bit. So here's my temperature. Here's my 0 degrees C. And so if I take ice, let's say that this is the point right here, where this is minus 20 degrees C. So if I want to start melting the ice, what do I have to do? The first thing that I have to do here is that I have to warm up the ice. So then I'm going to say here is that then I have this. I have to come in here and I have to warm up the ice. So this is warm up ice. And then what happens here is that I can't start melting till I get to 0 degrees. So then if I come along here to this point right here, then what I can start to do here is that now I start the melting process. So I'm moving in this direction. And then let's say that I warm up the water. Let's say that I come up to here, and let's say that I warm up the water to, I don't know, how about 20 degrees C? So what you're seeing here is that now in this process here, now what I'm done here is that I warm up melted ice water. So what you're seeing here is that there's 3 regions. And the way the regions look like is that you're seeing that here is a temperature change. So therefore, because I have a temperature change from minus 20 to 0, this has to be specific heating. Now, because I don't have any temperature change here, then this type of heating is now latent heating because I don't change the temperature of the ice until it's all melted. So then if I look at what happens next, you could see that in order for me to heat it from 0 degrees to 20 degrees C, I have to change the temperature of the water. So in this situation, this has to be specific heating. Now I can do the other way around. So now what I'm going to do here is that I'm going to cool down water from 20 degrees C to 0 degrees C, and then lower the temperature of ice to minus 20 degrees C. So now if I look at this thing, what does it look like? I'm going to follow the same graph here. So if I do that, I need to come all the way down to here. And let's see what happens. This is longer, but I'll adjust it as I move it. So now here I go. So here's T, here's 0 degrees C, and then right here, this is minus 20 degrees C. So what do I have to do here? So the first thing that I got to do here is that I have to cool the water down. So as I'm moving this way here, you're seeing that I'm cooling water. And now I start the freezing process. So if I start the freezing process, the length of these two blue lines have to be the same. So in this case, this is the freezing process. And then what happens here is that you could see that I have these 2 points. And then what I'm going to do here is that then I'm going to come back down here all the way to right there. So when I look at my lines here, you could see here is that this guy's at 20 degrees C. This line represents minus 20. So then it's moving down like this. And this is where I'm now cooling ice even further. So now I'm going to look at my bar diagrams. So if I look at my bar diagrams, it's going to come down to here. And then over here, it's got to come down to here. And then down to here. So now I have the lengths of my bars. So here I go. This is my specific heating to reduce the temperature of the water. The difference between heating it up and cooling it down is just the sign. So it should be the exact same number. Specific. And then I go in and I start phase transitioning. So if I start to phase transition, then we know that we're looking at latent heat of fusion. And now because we're cooling cooling ice down, I am still changing the temperature of the ice. So then this must be specific heating. So when I look at this latent heat, it should be the same value where latent heat of fusion is 3.33 times 10 to the 5 joules per kilogram. That's what we mean by that. Now I can do the exact same thing with latent heat of vaporization. So let's look at that. So now I have latent heat of vaporization. So here what we want to do is that we want to heat water, let's say at 18 degrees C to a boil, vaporize it, and heat up the water vapor. So if I'm looking at this graph, it's going to be different than this. So I have to change my temperature readings. So here's what I see here. So now if I look at this guy, I'm looking at it like this. So here's my temperature scale. And let's say that this right here is 0 degrees C. So this thing does not start at 0 degrees C. It starts at 18 degrees C. So now what happens here? I'm going to have to change my scaling as I go along. So here I go. What I do here is that I start my heating. So this guy, I have to phase transition all the way till this gets to 100 degrees C. So what I'm doing here in this situation is that I heat water, okay? And I'm moving in this direction. Now, when I get to this phase right here, what am I doing here? I'm now going to start the boiling process. So as I start the boiling process, I'm going to continue to move. Let's see, let's not do it for that long. It's going to look something like this here. So I'm moving in this direction. So now what's happening here is that now I am in the process of boiling. And so the next step here is if I'm going to heat it up, let's say that I heat this up, and let's say that I heat this to, let's say, 120 degrees C. Then you can see here is that then what I've done here is that I now heat up the steam. So if I look at my bar diagram, what do I see here? Well, you can see here is that I got to come all the way down to here. And this is the amount of heating in order to change the temperature of the water. So in this case, this is what I would call specific heating because of the change in temperature. When you start the boiling process, then the temperature does not change. And so as I mark this off here, then this becomes latent heating. And then the last one here, which is right here, you can see here that now I now come to specific heating because I'm changing the water vapor from 100 degrees C to 120. And then we can go the absolute opposite. So now here we want to go the exact opposite. So let's do this. So if I go the exact opposite, it's going to look like this. And here's my temperature. And I'm going to say here that this is 120 degrees steam. So this guy is going to be 100 degrees C, and then this guy is going to be 18 degrees C, and of course this is 0 degrees C. So then we could move through this process almost identical. So what am I going to do? I'm going to reduce the heat, the heat of the steam to 100 degrees C. So in other words, I had to cool steam. So I know that how much energy that took then has to be equal to this bar right here. The fact that there's a change in temperature, this is now specific heating. Now what's going to happen here is that I'm going to now cause a transition where I now go from boiling to go to liquid water. So again, we have two critical points, right? One where I go from hot steam to now forming bonds, liquid bonds. And then when I've stopped boiling, then I go the other direction here. So in this case, what am I doing? I'm now going to start I'm boiling. There's no doubt. This is boiling now. And I have to phase transition. And so you can see here is that as I move all the way here, I am now taking heat out of the vapor water mixture so that I have latent heat right here. And then finally, I'm going to cool this guy all the way back down to 120 degrees as I go in that direction. So now I'm cooling water. And how much heat did it take? It takes about this amount. So this is what I call specific heating.